Java has been around since the mid-90s and has evolved considerably over the years. One of the things that's changed is the way graphical user interfaces, GUIs, are implemented. The original method was the Abstract Window Toolkit, or AWT. This implementation acted as an abstraction layer on top of the operating system to standardize how various GUI components were actualized in Java. For example, a checkbox in a Microsoft operating system is implemented differently than in an Apple operating system than in a Unix or Linux operating system. The AWT gave Java programmers a common interface to use that took some of the complexity out of building GUI interfaces across multiple operating system platforms. The next innovation was the Swing library. Swing extends AWT by providing a more natural-looking GUI, as well as providing an enhanced toolset. The major difference is that Swing components are all Java-based and do not rely on any operating system code to perform the various controls. The latest GUI development environment for Java is JavaFX. JavaFX not only provides a platform for developing desktop applications, but also has a toolset for developing rich internet applications, RIAs, which will run on varied platforms such as mobile devices and tablets. In this section, we'll explore all of the GUI development methods and how they fit in today's pervasive computing environment. We'll also explore multi-threading this week. Throughout the history of computing, software development has been driven by hardware capabilities. The original computers were very limited in their processing power, and that limitation affected how much software could accomplish. As machines became more powerful, software was allowed to become more sophisticated by taking advantage of these power increases. Today's computers have very powerful processors, often with multiple processing cores on a single physical chip. We're also seeing a rise in the number of massive multi-processor machines, or MMPs, where there are arrays of many physical processors harnessed into a single computing entity. As before, programming evolved to take advantage of these hardware advances. Imagine the processing behind an application like Microsoft Word. In Word, you could be browsing your folders for a file to open while spell check is running, while an additional file is printing. Each of these tasks is referenced as a process, and each process has a series of steps to be performed called a thread. In fact, a given process might actually have many threads that it needs to execute to achieve a given goal. It seems to us mortals that all the running tasks are occurring simultaneously within our computers. However, that's not the case. Processors are single-threaded. They can only process one string of instructions at a time. The way we achieve the illusion of simultaneous execution is by sharing the processor's time among all of the running tasks. Task A gets a little time, then task B gets a little time, and so on. This situation can cause a bottleneck and slow down processing if there are a lot of threads waiting for the processor. To combat this bottleneck effect, we can build our programs to take advantage of the multiple processing cores available in the machine. This type of processing is called multi-threading, or sometimes concurrency. The trick to multi-threading is to make sure that the various lines of execution occur in the order we're expecting. For example, we could not begin reading data from a file before it's been opened. This section of the class discusses how to implement multi-threading in your program code.